So we will talk about polynomial and rational inequalities today. And to begin with, this is a little bit different in the sense that it's not just linear. We can't isolate x real easily. In fact, when we solve this, the basic concept of solving quadratics, as we've talked about, is taking and factoring. Now, the difference between this and solving just a linear equation is that we have a product here, and that's going to mess things up just a little bit. I prefer to start looking at this in a graphical manner. So I know I have an x-intercept of 5 and an x-intercept of -3 in this problem. And I know because I have a leading coefficient of 1, this parabola is going to do something like this. And what this is actually asking is for what y values, because all this describes a y. Are those or for what x values are those y values less than 0? Well, this graph is less than 0. The y values are less than 0 here. All right. And if I was to state that answer, those are the x values from -3 to 5, but not including. This would be my interval notation. All right, so I can get it off the graph pretty easy. How do I get it out of the algebra? Well, I say, well, I know they're going to equal 0 at the two intercepts. So what I usually do is I'll put down a 5 here and a 3 here, and this is like a number line, right? And then I'm going to run a test on each interval, both between and outside those two axes points, because I know due to multiplicities that my graph's going to go through the axis there, and that when it goes through the axis, it becomes either negative to positive or positive to negative. So if I test a point out here like f of 10 and look at these two values, that's a positive and a positive, which ends up being a positive. So this is greater than 0, not what I'm looking for. I'm looking for less than 0. Between, I'm going to look at f of 0, and I get a negative and a positive, giving me a negative. This kind of checks off what I'm looking for. And then let's go with a -10 here. And I get two negatives, which again is a positive, which is not what I want. So from this testing of the number line in the root situation, I get the same answer because these are both open circles that can't equal each other. I get the interval from -3 to 5 as my solution for the x values that leave me a y that's less than 0. I find that helps at least with quadratics. Now cubics, we know how to graph cubics as well, but I'm going to not even graph this time and spend the time doing that, and I'm just going to use this new concept of factoring. First I'll pull out the GCF, and then I'll take my difference of squares. And now I know that this graph is going to cross the axis at 0, 4, and -4. And it's also going to equal 0 in this case. I want to know when things equal 0, so I'm going to put filled in dots here. And then I'm going to test the intervals outside and between my intercepts. So again, I'll test 10. I like that number. I get 3 positives, which is positive, and this is good for us because we're looking for things greater than 0. Try f of 2. I get a positive, negative, and a positive, which ends up being a negative, which isn't so great. And then I'm going to try a -2. And in this case, I get a negative and a negative and a positive, which is a positive, also not so great. And then I get f of -10, let's say. And those are 3 negatives, which end up being negative. So this is good as well. All right, now I'm going to state my answer in interval notation, but in this case, since it was equal, I'm going to pick the positive values once again and include the numbers at each endpoint. So -4 inclusive to 0 inclusive in union with 4 to infinity, and that will be my solution. Obviously, infinity can't be contained, so it's not included. Here's another one. Again, though, what we want to do is we want to set aside to 0. So I'm going to go x cubed plus x squared minus 6x less than 0. Notice strictly less than this time, so we won't include those endpoints. Factor out an x, get x squared plus x minus 6 less than 0. X plus 3, and x minus 2 less than 0. I'll go ahead and write -3, 0, 2, check points, f of 10, f of 1, f of -1, f of -10, 3 positives, leave me with a positive. It's not what I want. Plug in a 1, I get a positive, and a negative, which is a negative. I do want that. Plug in a -1, that's a negative, a positive, and a negative, which is a positive. Don't want that. And then -10 gets me 3 negatives or a negative, which is what I want. Now again, I'm not going to include these values because that's where it equals 0. So I'm looking for my negative answers, which are from -infinity to -3, not inclusive, in union with the 0 to 2. So those are our polynomial inequalities. Let's move on to our rational inequalities. Now, here we have to consider something totally different. We know in rational functions that we have these things called asymptotes. And in this problem, just from what we know we've got asymptotes at 2 and -2. So think about what typically happens with asymptotes. We graph something, and I'm not guaranteeing this is the graph of this function right here, but we usually do something like, something comes here, and then it could do something like this, I don't know, and then maybe something like this. So not only do we have things changing at x-intercepts, which we did in our polynomial function, but things often change sign after moving over the asymptote. So we have to consider asymptote values as critical values, okay? And that's what we're going to start calling them. So we factor this, get a 2 and a -2. We're going to have critical values of plus and minus 2, and the intercept, the x-intercept of 3. So now what I want to do is, again, I want to test all those values. So I have a -2, a 2, and a 3. So I'm going to look at f of 10, f of 2.5, f of 0, and f of -10. Pop all those in. And again, I'm going to just look at the positives and negatives. So I have a positive, and a positive, which gives me a positive. I want values that are greater than or equal to 0. Remember, this 3 can equal 0. These guys are not included because they're asymptotic points, right? So this is what I want. I go to 2.5, I get a negative on top, positive, and a positive, which ends up being a negative, and I don't want that. Then I plug in the 0, I get a negative, and a positive, which is a positive, and I definitely want that. And then -10 get me 3 negatives, which is a negative. I don't care for that. So now notice where the positives are going to be my values. I can't include either one of the 2's because the function's undefined there. So I go from -2 to 2 in union with, I do include the 3 because x can equal 3 since it's an intercept. to infinity, which obviously I can't include. And this is a similar problem, however, the side's not equal to 0. So what I want to do is I don't want to, let's put it that way, I don't want to get rid of that denominator because that's going to play a part in the problem. So I subtract the 3 to the other side, get a common denominator of x plus 2, multiply that by the 3. It's less than or equal to 0. This goes to, let's see, negative 2x and a negative 6 over x plus 2 less than 0. So I have an x-intercept of, what is that, negative 3. I have a vertical asymptote and negative 2, so my critical values are negative 3 and negative 2. Pop those on a number line. Check values of 0, negative 2.5, and negative 10. We'll note here that at 0 I get a negative over a positive, which is a negative, and I'm okay with that because I want negative values. Can 2 or the negative 2 be included? No, so I'm going to open circle that. Negative 2.5 is going to get me, let's see, that's positive 5 minus 6 is a negative on top and a negative on bottom, which is a plus. Don't want that. Negative 10 gets me a positive on top and a positive on bottom, which is positive. Whoa, is that right? Negative 10 gets me positive on top and a negative on bottom. Thank you. Which is a negative. All right, and I want the negatives. So again, I look at the value of 3 and say, can that, or negative 3, can that be included? It can, because that's an intercept. Put a dot there, and I want the values that are strictly less than. All right, so I don't want 3 in the problem. I want less than that because 3 gives me a value of 0. So in this case, I will say from negative infinity to negative 3, because 3 gives me 0 once again, and I don't want 0, I want less than 0, in union with negative 2 to infinity. And finally, something that's completely factored out. This will actually be a little bit easier. In this case, I have critical values. I can write right off the bat of, let's try to do them in order, negative 7, negative 5, 1, and 2. So I go through, I list those critical values, negative 7, negative 5, 1, 2, pick f of 10, f of 1.5, f of 0, f of negative 6, f of negative 10, pop them into this equation. The 10 gets me, obviously, everything's going to be positive, so that's positive. I want greater than 0, that's good. 1.5 is going to give me a positive, negative, positive, positive, which is a negative. Don't want that. 0 gives me a negative on top over a negative on bottom, which is a positive, and I don't want that. Negative 6 gives me a negative, negative, positive, negative, 3 negatives, which is a negative. And negative 10 gives me all negatives, which is a positive. And I want that. I can only include values that are not asymptotes, so that's an asymptote. That's an asymptote. These are intercepts. They could be included if I want them to be included. and this is greater than 0. So in this case, they're not going to be included anyways, but I just thought I'd label them anyways, make that a practice. We're looking for the positive answers, so we can go from 2 to infinity. Again, we're not including 2 because it has to be strictly greater than 0, and 2 gets me equal to 0. Negative 5 to 1. Whoops, to 1. Let's do it this way. And then from negative infinity to negative 7. And there's my interval notation for the answer. And that'll do it for today.